Hi, my name is Christoph Schröder and I'm from the University of Bremen. In this work, my colleagues and I analyze how varying stimuli and trajectory lengths influence the accuracy for eye gaze biometrics. In eye movement biometrics, we try to identify people solely based on how they look at things. On the right-hand side, you can see that the gaze patterns of two different users reading the same poem differs quite significantly. The same is true when the users follow a random moving dot. Gaze-based user identification is especially interesting for HMDs, where we can seamlessly and continuously identify people without the need for a dedicated login procedure. In this work, we present three major contributions. First, we extend the current state-of-the-art classification by George et al. From 2016 and improve its performance. Second, we analyze the influence of the stimulus that is used in training and testing and how the classifiers work with new testing stimuli that differ from the training stimulus. Last, we analyze how long the trajectory needs to be in training and testing to have an optimal identification rate. In our first experiment, we find that the stimulus, when it is the same for training and testing, does not have much of an impact for the identification rate. Also, when we use random decision forests instead of radial base function networks, the performance is slightly worse. Further, we found that without the feature selection procedure that was proposed by George et al., the accuracy increases in all configurations. This shows that at least here, random decision forests and radial base function networks work best with all features. In the next experiment, we train the algorithm on one stimulus, such as random moving dot, and evaluate the classifier on another stimulus, such as a poem, and then the other way around. We find that the accuracy drops significantly for all configurations. Two things are interesting though. First, the random decision forest has the highest accuracy in this experiment, which indicates that it might generalize better in a task-independent setting. Second, the performance is highly asymmetrical in that training on text and evaluating on random dot is much better than the other way around. In our last experiment, we take a look at how much training and testing data is needed. Our experiments show that with only 90 seconds of trajectories for training and testing, an accuracy of over 85% can be achieved with our best classifier. To conclude, first, we improved the state-of-the-art classifier by 5.2 percentage points. Second, none of the tested classifiers is capable of true task-independent gaze-based identification. Last, we found that only 90 seconds of gaze data suffice for over 86% identification accuracy. All our source code is available on our homepage. Thank you very much for your attention.